We're going to talk about heating curves now. What is a heating curve? Well, it talks about the substance, okay, and whether it is a solid, a liquid, or a gas, and at what temperature your sample is existing. And we know certain things. We know at this 1 atmosphere, we must be working with something like water here. Oh, yes, we definitely are. See, there's that number that we just got through talking about. We know that the water will be a solid as long as you are below 0 degrees Celsius. So all through here, as you're heating it up, because it was really cold, we're heating it up, it's still a solid though. At a certain point, it starts melting. It melts and stays at 0 degrees Celsius. Then, once all of it has melted, it's going to start warming up again because we're still putting in more heat. Eventually, you will get to a boiling point, 100 degrees Celsius. Then you'll boil, and it'll stay at that temperature until all the liquid is gone. And then you can start heating it some more and make the gas even hotter than it was when it came off of the water to begin with. Now, these numbers, here's the amount of heat you have to put in to change a mole of water into, well, water instead of ice. Then how much energy do you have to put in order to change from liquid to gas? Ooh, a lot more. Here is the amount you have to use, how much energy, just to heat it from 0 to 100. It's all liquid. Oh, that's very interesting. The numbers are really quite fascinating because of the size of them. It takes less energy to heat it from 0 to 100 than it does to turn it into gas by a significant amount. But this is called a heating curve, and it shows you the different numbers associated with changing something from a solid at a particular temperature to a gas at a particular temperature. And sometimes you'll just be interested in a subsection of it. So variation in temperature as you add heat. The ice was very cold. It's still ice until it gets to 0. They're still locked together. They might oscillate a little faster, but they're still locked together. You know, they might be going like this versus this, jiggle, jiggle, or jiggle, 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 but they're still locked in place. Then once they start melting, then some of them start tumbling over each other. When all of them are able to tumble freely over each other, then you're a little liquid. So once you get to that melting point, they're going to start moving past each other. Those attractive forces are no longer sufficient to hold them in place compared to the amount of energy as heat in there. As you go, you've finally broken all of those attractive forces that were trying to keep it as a solid. That's where we are right here. So boom, we break them all, and now we can start warming up the water. We're just warming up water. It still looks like water the whole time, but it's going from cold to hot. And you can keep going here at that boiling point. It's now going to stay at this constant temperature as it boils away. Once you get to here, then you're finally going to have some of them start breaking away, get away. Now we're finally all getting away. Now we can heat up the gas. Now, they have different parts labeled. Here's a graph. It's supposed to be a heat graph. Where is the heat changing, but the temperature not changing? So we have to remember what was on the graph. This one was temperature. This was heat. We were adding heat. But sometimes adding heat didn't change the temperature. Phase changes are when that happens. So, okay, they want the heat to be changing, but the temperature not changing. Well, since this is temperature, I want any place where it's just a flat level surface. So here at 2 and here at 4. Now you'll notice that sneaky so-and-sos, they put 4 in here. And you might, if you didn't read all of them, you might pick that. Now make sure you read everything, because that's the better answer, both of them. When we're measuring heat, a lot of times we have to use heat capacity. And there are multiple ways of talking about heat capacity. Specific heat is where you're just talking about the heat compared to the mass. So per gram, for example. The molar heat capacity, you're comparing the heat to the number of moles. Now, in water, we have this specific heat. This is 4.18, and if you looked, you could find it 4.184 joules per degree Celsius and also per gram. Whereas if you're looking at it in terms of a molar heat capacity, you're going to find 75 joules per Kelvin and per mole, okay? Now there is no difference here with the degrees Celsius and degrees Kelvin because those degrees are the same size. Think back to what we were talking about in chapter 1. The size of the degrees is the same. And you're always talking about a difference in temperature, so you don't care about the absolute temperature. And they get used in the following equations. If you're doing a specific heat, you're going to use mc delta T. If you're using a certain number of moles, you'll use moles C delta T. And of course, they are slightly different because one of them is per gram and the other's per mole. So that's what's up with that. All right, here it looks like we're going to have a little quizzy question here. What's the most difficult to heat or to cool? This means we have to understand what the numbers mean. I'm trying to change the temperature. Which one is going to make me work hardest to do this? All of these have been given to me as a specific heat, so it's a per gram. They haven't said specifically, so I'm going to have to sit here and think about this for a minute. I guess I should just assume they're all 1 gram samples, because otherwise it would depend on how many grams there were. All right, so here's aluminum, copper, benzene, and water. The most difficult, the one that I'll have to work hardest at. Oh, work. Oh, yeah. That's that energy thing again. I'm going to have to put in the most energy for the water. There it is. Absolutely, it's the water. If we need to calculate the amount of heat in order to change the temperature, so I want to change the temperature, I know I'm going to have to put some energy into it, right? Here's 2 different ones. Calculate the heat necessary to raise the temperature by 20 degrees Celsius, which would be 20 Kelvin too, for 100 grams of water or 2 moles of water. Okay, I'll have to use 2 different heat capacities, specific heat, right? So on the first one, it's grams. So I'll use the specific heat capacity and I'll use the one that has mass in it. Well, they told me the mass, it was 100 grams. This is that 4.18 we were talking about. And we're going to change it by 20 degrees. Just multiply them together. mc delta T. There we go. Now the second one is in moles. So I have to use the molar heat capacity. So we'll use the number of moles and then C sub m and delta T. You can see the delta T is the same for them. And then I find out this. It makes sense though that this should be more than that because remember a mole of water is 18 grams. So 2 moles is only 36 grams. This is 100 grams. That's a lot more. So yes, this is a lot more than that. And just remember, the delta T is the same whether you're in degrees Celsius or Kelvin because the degrees themselves are the same size on a thermometer. So we are following a crazy hiker. He likes snow camping, all right? Personally, I think that's not that much fun, but here he is. He's decided to go camping in the snow. And he wants to have hot soup now. He wants to have this soup. And he's starting with snow. He didn't carry water with him because it's freaking heavy, right? So he's starting with snow, and it's negative 18 degrees Celsius out. Like I told you, this guy's crazy. He's out camping in this. And he puts it in a pan, and he needs to heat it. And he needs to heat it to boiling to make sure that he doesn't have any germs in it, right? So what does this mean in terms of a heating curve? Well, first of all, it means that he has to heat the snow up to the melting point, right? Then he's going to have to put in enough energy to melt it. Then he has to heat the water itself up to the boiling point. Then we'll be boiling the water and then he can actually make a soup, right? So we're just going to draw this on a situation. Here's where he's starting, this negative 18 degrees Celsius. He has to heat the snow until it finally starts melting. Then he has to melt the snow. Then he has to heat the water up. And we're going to stop right there because we don't know how long he's going to boil it. I don't know whether he's putting carrots in here and it's going to take 20 minutes or what, right? We don't know about this. So this point is going to be our goal. Once it's boiling, we're going to say, good, we're done with this problem. So just to clarify, here we are heating the ice. Heat ice. Here we are melting ice. And here we are heating water. So I have three things I want to add together. All of them involve 275 grams of H2O. This was as ice, this is melting, this is as water. The water itself has a high specific heat value, so we're going to expect to get some pretty big numbers out of this. The water absorbs large quantities of thermal energy. Well, that's the same thing as saying that. It is a heat sink. Really hard to get it to change temperature, which is why we use ice in our coolers when we want to keep our drinks cold. We go camping in the summer. So it can absorb energy without changing phases or changing its temperature very much. That's the whole idea behind the heat sink. All right, and why? It all goes back to the hydrogen bonding we were talking about earlier in the semester. So let's do this now. I have to go look up some stuff in order to do the problem. If I look up ice, I'm going to get different numbers than if I look up water. So ice, since they gave me grams, I will go look up the one that has to do with grams. I find out it's 2.11 joules of energy per gram degree Celsius. If I look up water, and this one honestly you might want to just memorize, 4.184 joules per gram degree Celsius. We aren't going to steam, but if we went and we looked up steam, we would find out that it also had a different number. It's 1.89 joules per gram degree Celsius, but we aren't going to worry about that, okay? I'm going to be using these two. So what do? I need to use this one for this section. This is the one that I'll use for that section. This section is where I will use this. What about this guy? Oh, this is the change of phase one. Oh, yeah, the change of phase one. Got a triangle. So for this one, this is change of phase, and it has a different formula than the other two do. There's no delta T in it because the temperature isn't changing. It's staying at 0. That one's different than the other two. Those units won't be there. It'll just be joules per gram. No degrees Celsius involved because there's no change in it. I'm going to call that 1. I'll call this 2. And I'll call this 3. So we'll do this in 3 parts. For section 1, I'm heating the ice. What is my change in temperature? Well, I went from -18 to 0. So as far as the change in temperature, it's T final minus T initial. So that would be 0 minus a -18. Oh, okay, 18 degrees Celsius. Great. And I already know it's 275 grams. So I can just go ahead and say 275 grams times 2.11 joules per gram degree Celsius and times 18 degrees Celsius. And we see the grams cancel and the degrees Celsius cancel, and we'll be just left with joules. This is that formula where you're talking about M, Cm, delta T. That's what this is. So the amount of heat is going to be the mass, the specific heat, and delta T. There they are. If we calculate that without worrying about my sig figs at the moment, okay, I get way too many sig figs, but that's all right. This is joules because I've canceled the other units. Section 2 is the odd one, right? It's just a change of phase. So there is no delta T in it. I'm just talking about the 275 grams, and I wasn't given anything that was in grams. I was given this 6.01 kilojoules per mole. Oh dear, nothing cancels. Oh, but it will if I multiply and I have moles and grams, right? Because then the moles will cancel and the grams will cancel. Well, this is the molar mass upside down. Oh, okay, 18.01 grams per mole. I just put it in like that, and then I will get this. Now notice, this is in kilojoules. This is in joules, so we're going to have to be careful with that. If I do this in kilojoules, I get 91.819 kilojoules. Maybe I should write 91,819 joules. Holy crap! Look at how much energy it takes to melt it compared to heating it from 18 to 0. This is all taking place at 0 degrees. And then in section 3, we're going to go back to using a Q equals M Cm delta T again. All right? So that's the 275 grams. And this time it's multiplied by the 4.184 joules per gram degree Celsius. Grams can already cancel. And then I wanted to heat it. How much? From the melting point to the boiling point. So you might not have thought about that. But yes, they didn't tell you that because they're expecting you to know what the melting point and the boiling point of water are and know that that's what we're doing here. Sneaky. So this ends up being 115,000 joules. Holy Toledo! That is not very much more than it took to melt the whole stuff. We go from freezing to boiling. Not much more energy than just melting it. Really quite astonishing. Again, this is why you end up using ice in your coolers if you want to keep your drinks cold. Okay, so we would end up adding these three. So the 10,445, the 91,819, and the 115,060. You add all those up, you get a ridiculous number. And then you have to say to yourself, well, just how many sig figs do I really have? And when you look at all the numbers that they gave us, we have to round this to 3 sig figs. So 217,000 joules, or shall we say kilojoules.